Okay, I think we're going to soon get started. Everybody can get a seat. Excellent. I've been told that I should introduce myself. So my name is Alain Goriely. I'm the professor of mathematical modeling, and I'll be talking about mathematical modeling. Today is a special day. It's a special place. We are in the Andrew Wiles building. It was opened a year ago, and it has become the focal point for mathematics, but also for a lot of different activities. So it's wonderful to welcome you. And as I said, Andrew Wiles is also a professor here, and gets a lot of mail randomly addressed to Andrew Wiles at Math. And it's a special day, not only because we have the pleasure of your company, but it's also a special day for Andrew Wiles. Here I found a stamp from the Czech Republic celebrating Andrew Wiles. And you see here, it's the Fermat's last theorem. And it says here, Andrew Wiles, 1995. So that was about 19 years ago. But what is maybe more interesting is that it was the day in September 1994 that Andrew Wiles made the final discovery that allowed him to finally resolve the problem and prove the theorem. And we know exactly when, because he remembers. And that day was the September 1994. So exactly today is 20 years, the 20-year anniversary of the discovery, which led him to his fame, the proof of the theorem, the creation of the building, and so on. So it's all related, a chain of events. Okay, but we're not here to talk about interesting mathematics like Andrew is doing in number theory. What I really want to talk today about is our mathematics is related to science, society, engineering, all other areas of knowledge. So my talk will be divided into roughly 3 parts, and I want to have time for discussion. First, I will share general thoughts about the act of modeling, what we actually do, very general thought and remark. I'm not going to go all philosophical on you. I just want to be very pragmatic. Then I will see how these ideas apply to the climate, take the climate modeling as an example of how to implement some of these ideas. And maybe we'll learn also something about how people actually do the modeling of climate in the process. And then I want to tell you about problems that I've been working over the last couple years or so. There'll be something to save the planet, something to save mankind, and just something for the beauty of it. And data reserve, you'll see exactly what I'm talking about. So let's start with some general remarks. And I'm going to start with some remarks from Lord Kelvin, here also seen in a stamp. Here is a stamp from West Africa. And Lord Kelvin was very interested in applying ideas of mathematics and generally physics to the world. Here you see the Great Eastern. He was actually on the boat that laid the first oceanic cable between Europe and America for the telegraph. And Lord Kelvin, talking about science, about modeling, says the following thing. I often say that when you can measure what you are speaking about and express it in numbers, you know something about it. But when you cannot express it in numbers, your knowledge is of meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely in your thought advanced to the stage of science, whatever the matter may be. So he said, if you really want to make progress at the scientific level, you have to translate the idea into mathematics, into number, into quantities for which you can make a very specific statement. He also said, in science, there is only physics. All the rest is stamp collecting. So not all his ideas. He also said another time that vectors were completely useless and things like that. But OK, we'll take what we can. Lord Kelvin is certainly a great mind. So what does it mean by all in science there is only physics? What's the idea of physics? And it was very in a broad sense. It was really natural philosophy in the 19th century. So the way physics approach a problem is, call it the physics paradigm, is the following, where you start with some data, then you identify some patterns, and based on first principle, you would go about that patterns and write a model for it. And the simplest and classical example for that is the evolution of celestial mechanics, where we start with Tycho Brahe in the 16th century, and who catalog numbers, look at planets, and look at the position in the sky. A very extensive table. So that was really data gathering, what we would call big data nowadays. Then after that came Kepler, here also, West Africa stamp, who says, I'm going to look at this data and what is going to do what we do today, which is called statistics, analyze the data, trying to extract laws directly from the data. And that's how Kepler came with Kepler's law, like planets go around in an ellipse and so on. Okay, very deep and profound. But then came Newton, who wrote a mathematical based on simple physical laws. Right? He had to find the laws himself, of course, because he did both. He says, if I apply simple physical laws, essentially F equals ma with the right force, gravitational force, I can explain all of it. I can explain Kepler's law, I can explain all of it and much more. So summarizing into a few equations, a mathematical model, all of the knowledge that is required to do celestial mechanics. Okay, here is a stamp that I found from the Benin, which is actually the same country as the Dahomey, but it was the République Populaire du Benin. That was during its Marxist-Leninist time. So they also evolved from Kepler naturally in 20 years to Newton in this stamp. So, but when you actually do modeling, you do it as a profession, turns out that the physics paradigm, that's why we put in textbook. But the reality is quite different. What do? Well, we do start with initial data, some observation. We have a friend who's a biologist or geophysicist or material scientist says, look at this, I have this nice experiment. Say, oh, that's wonderful. And so you go back and with your student, you say, okay, let's write a model, and we're very happy with the model. Then you go back to the scientist and you say, okay, here is a model, can you tell me? And it shows you more data. And invariably, the model is wrong, the simple model. It never happens, it's right. Now, you have to go and explain to your poor first-year student that he's making great progress because his first model is already wrong. But the real problem, I show you, wrong models is fine. You really understand something. Often, it may seem strange, but often the wrong model tells you more about the nature of the problem than a correct one. But the real question is, why is the model wrong? What did we miss? What are the important physics or important chemistry or important aspect that is not in the model? And so you create a new model, and the model invariably also has more variables, more parameters. You start throwing things. Maybe there is an effect here that we neglected. Maybe there is another scale that came in the problem, and so on. So you go there. And then you go back and discuss and try to validate with the model with new experiment. Then you see, is the model self-consistent? Does it provide me any insight, or does it correspond to other data, or the system, or the experiment in the literature? Do I understand? Does that make sense, essentially? And if it does, you can do two things. You can do a simpler model, throwing away the stuff that may not be important, or you can say, no, I really want to predict things, and you'll make a much more complex model. So you can go both ways. You can go do a little bit of math or a little bit of engineering or computational science. Let's put that on a big computer and see what happens. And then you go back, you try to validate, make more experiments, and then you refine the models based on that. And then maybe eventually you may have some prediction and predictive value for the model. And then when you do that, you go back here, and then you start this loop again and again and again. And when it comes to the climate, this loop has been done hundreds or maybe thousands of times, trying to refine based on ID and move on. But the question is, we have a model. How do we know how far we should go? What is a model quality? And there are two important aspects, quality and complexity. So quality can be, for instance, the predictive value. And we'll show you an example of what I mean by that. Complexity is really the number of things you've added in your system, the number of parameters, the number of variables. How big is your system? It turns out that if the model becomes very complex, usually you lose in quality. It's not because you take into account all possible effects that your model is actually better. There is a point where you add things and it gets worse. And why is that? There are many different reasons. One of them is computational time, of course. We know that computational time, the model becomes complex, then the computation time required to get an output out of it becomes increasingly large. Okay, somewhere maybe we've been here in the 60s. This line is always moving up. We know that computers are getting faster and all that. But the other problem, and that's what I call insight, is that as your model become more complex, you can do more things, but you understand less. Okay, you know something, you get a number, you get the temperature in year 2100, but have you understood something about how the system or the climate works? And it's usually with the little system that you really gain understanding about the system. It's with the larger system that you can do prediction. So what you really want is to have model and study them in that whole range from different sides, small, medium, large, extra large. But you want to try to avoid the American way, the extra, extra large right here, right? Because the quality of the model decreases, you take an infinite long time to compute anything, and you don't understand what you're doing. So you really want to work in that range. So let's see how it works on more practical example. So now I want to apply this basic concept on climate modeling. So let's start with the simplest possible model. And that's what in physics we call a back-of-the-envelope models. So that's for the younger audience. At some point in time, there were stamps, and they were put on little piece of paper we were called envelopes to send to somebody else. So the envelope and the stamps, as you saw, are very important for us because they contain information. When you receive it, you can do computation on the back of the envelope. And so the basic computation when it comes to the climate is the following. Let's just look at how much energy is coming from the sun. There is really very few other source of energy, maybe from inside the Earth, but it's a fraction of a percent. It doesn't matter. So let's look at the energy coming in, the flux of energy, 342 watts per square meter. And we know that the albedo, the reflection of the planet, is about 0.3. So that's because we see it from outside, that means photons are coming out. So you lose energy, right? And that's about a third is reflected solar radiation. There is nothing you can do. It's gone. And so the back-of-the-envelope computation say, well, obviously, the difference, because energy is concerned, is that the Earth reflects 235 watts per square meters. There is no discussion about this. This is basic physics. Okay, so that's very good. Now, you can go one step more. I said, we know from physics that a black body, like a planet, is well approximated by what we call a black body, whose flux of temperature is proportional to the temperature to the power 4. And so if you look at that, if you play with these numbers, you'll get to the following prediction, is that the temperature of the Earth should be minus 18 degrees on average. Well, it turns out the Earth is about 15 degrees. So the error is only 33 degrees. Okay, that's great, first wrong model. What have we learned is that there is some energy that is trapped inside, and that as a whole, it doesn't work as a black body. There is something. And that something is the atmosphere, and it's the greenhouse effect. So somewhere in the modeling scheme, in my model diagrams, we really down here. We've learned a lot, is that we can only understand the temperature on Earth if we take into account the atmosphere, not just the physics of energy. Okay, so we understand a lot, and the prediction is obviously completely wrong. So we can start a little bit more complicated. We can say a one-dimensional model. So what happens is the energy comes here and bounces back and forth between different layers of the atmosphere that have different chemical composition. And so you can do that balance, which is called radiative forcing, how much CO2, for instance, the most important one, with reflect energy coming at certain wavelengths to other wavelengths and so on. And you can do that computation. And for instance, you would get that from that simple computation, you know that if you double the CO2 content in the atmosphere, then you would automatically, on average, get a temperature of 1.1 Kelvin. There is no discussion. Nobody discussed that. It's very clear that this is not controversial at all. They said, but if you do the computation based on that, you'll get the wrong result as temperature in different zones, or even the average temperature, is because there is another effect that we have not taken into account, so that model also fails. There is another effect that say the latitude effect, that the poles are colder and that the equator is much warmer. So the radiative forcing taking place there is quite different. So you say, okay, now I can't just do a layer here. I really have to take into account the transfer between these different zones. So you would go about, so we are here, we are about here. We have a prediction very poor, but now we know that greenhouse gas is very important for anything related to the atmosphere, and you can make very good prediction based on that. Now you say, okay, now I'm going to consider a different zone, and by convection, warm air goes up and cold air goes down. I can start computing the motion of the mass of air with different temperature in different zones. And what I would use in this case is very simple equation, actually, the set of 1, 2, 3, 4, 5 equations that comes from 19th century basic fluid mechanics, and this one is from thermodynamics. That just, essentially, it's a reformulation of F equals ma, telling you the velocity of air in different zones based on the forcing F lambda, F theta, and the rotation of the Earth. These are really, they call primitive equation when it comes to atmospheric science. They're the basic equation. Nothing, you can't escape physics at that level. It just say things are moving from one side to the other one. The global mass is conserved, and the thermodynamics is a statement about conservation of energy. So these are 5 equations that describe that, and you can run them on different zones. We say, okay, now if I can run them on different zones, I can probably run them on a finer grid. Now, instead of looking at 3 zones, I can say, now I want to go a little bit further. I'm going to run the same equation of transfer of linear momentum, transfer of mass going from one to the other one, but on a grid that spans the entire Earth. And that a typical grid would be a few degrees by a few degrees. So I make a little box and I say, how much mass is going from one to the other one, how much energy is going to the other one, and so on. And I can put that on a computer. Where I say, well, if I can make a grid like that, as long as I'm going, these are called general circulation models. These are the typical models used. If I can go like that, well, I can also look at the level in the atmosphere, and I can have up to 30 typically level of atmosphere. So I make box, and I just say each box exchange energy and mass with the other one, and so on. And that's essentially all there is into these climate models. But it's how we do it that is important. So an interesting computation is to see how many computation do we have to do to get any answers. So let's compute together. So I told you we have 2.5 times 2.5 degrees. That's about 10,000 cells, 10,000 boxes. In each box, I define the velocity going north, the velocity going east or west, right? And the temperature there, and the humidity, typically. You can reduce that for 4, 5, 6, 7 variables. 7 variable is kind of standard of what you need to get all the information about how temperature moves from one to the other, what are the mass that moves, and so on. So 10,000 cells, that's just for the mapping the Earth. Now I want to map the atmosphere also, and I say about 30 layers in the vertical direction, and so that's about 300,000 grid boxes. So now I have 300,000, that's good, but I have at least 7 unknown: velocity of my mass in south, north, east, west. I have the temperature, I have humidity, and a couple more. Okay? So that gives me 2.1 million variables. Okay, now that's starting to add up, or multiply up really in this case. Now, if I assume 20 calculations for each variable, that means if I want to know the velocity at one point, I have to do 2 multiplication and 1 addition and blah, 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 do a certain number of operations. 20 is actually very low. If I have to do that for each variable, that how many times my little CPU has, how many operations it has to do every time it wants to compute, that's about 20 computation. That means 42 million calculation per time step. So if I just want to know how things evolve, the temperature, let's think of the temperature, evolve from one time step to the next time steps, I will have to do 40 million computation. It's very easy nowadays, 42 million, right? We do, gigaflops, megaflops and all that, megaflops, million of operations per second. So it's very doable. But then, of course, the time step is only 30 minutes. Or There are plenty of ways to estimate time step and all that. That's the typical time step. But what we want for climate is we really want to know the climate up to 2100, 100 years in the future. Okay? So you need 2 billion calculations per day to move the system, the model for 1 day. And then you need 100 years of simulation. So you multiply that, blah, 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 and you get about 73 trillion computation that you CPUs have to do. That's quite a lot. It's quite doable, but it's getting very expensive. And of course, as long as you're there, you want to add other effects, ocean and ice, or the interact, or the effect of aerosol, the chemistry, the biomass, the hydrology. So by the end, what you want is so-called an Earth simulator that take all these aspects, all these boxes, all the chemistry, the geochemistry of the ocean, the interaction with the ice, and so on, and then putting all together. And that's why you need supercomputer, or the people who do climate science tell us they really need very big computers to do that. And contributing to global warming, of course, because these computers, it takes a little town just to power them up. That's why they are in remote places and all that. I don't know. Nobody has done the computation, how much the computation of climate change is actually contributing to the effect. And I'm sure it's negligible, but it's pretty big already. Anyway, you do need that. But so you can do that, and people do that, and they're very refined ways of doing it. Essentially, tens of thousands of people have been doing that for years and years, trying to refine these models. But the real question now is, where are we? Are we really here, the best possible outcome in terms of model quality, or are we going down here where we've added so many effects that we've added so many errors in the numerical computation that we not really know what's really going on? And a lot of the arts of these very large, complex systems is really to try to estimate these. How much are we sure about the solution? So how do we know that the solution that we get is actually a good solution, a valid solution? So what you can do, so you want to do model validation, and it's always easier to predict the past than the future. So you can start by doing that. So here is a computation by one of these big models. And it looks back in the past. It said, let's start at 1900. And let's take care of this function, the little function f that I show you, at the forcing coming from outside. Particularly volcanoes turned out to be quite important in putting energy in the entire atmosphere. So here you have different volcano eruption, Pinatubo, etc., Santa Maria, from 1900 up to 2000. The black line is the recorded temperature evolution around that time. And the red line is an average of a lot of different simulations. And you see it is wiggly, and we're going to talk about the wiggle. But what you see, and it's also taking into account what we know about the increase of greenhouse gas over this time, the measure of all the greenhouse gas. So you see that you get a very good job at measuring, at getting the general trend. Of course, there are some years where the red line is not at all like the black line. That's why people say, you see, there is no climate change. Your prediction is wrong. But if you see the trend, there is no doubt. It's very good. It's very, very good on many different measures. You can do the same computation. Now you can do thought experiment and say, are greenhouse gas really that important? What if we keep them at the level of 1900? Maybe it's really the volcano that creates all that mess. Okay? So you start again, do the same computation with the volcanoes, but with no greenhouse gas increase. And this is what you get. You get no increase of temperature at all from the 1900s. So you know with very, very likely, almost certainty, that the greenhouse gas have been responsible for the evolution of these. Okay. So when you look at a model, it's an important notion of either predictability or uncertainty. So it's important to find a way, what do we really know, what comes into the model that messes up our computation if we want to do a projection. So there are 4 typical sources of uncertainty in climate projection. There is what's called scenario uncertainty. It says, well, we really don't know if the government are finally going to come to their sense and do something about the problem. So we don't know what's going to happen. We can run 2 scenarios. People are going to realize that we should stop using fossil fuel and do a lot of different things, or people are just not going to care. We can do this too, and anything in between we can run. Okay? There's model uncertainty. There's still plenty of people working on the physics of this problem. How does the ice interact with the atmosphere, with the water, and so all that. There is a lot of physics we don't quite know yet, and there's a lot of work to be done. So, and which are the effects important? So what is the best model? Then there is a lot of parameter uncertainty. You don't know the data perfectly. You don't know the parameter. You know the temperature maybe in a box, but that comes with a certain error and all that. So you have a lot of these. And finally, more important, more interesting for us, you have internal variability. And that's intrinsic uncertainty in the climate system. And that means in the model itself, whatever you do, even if you had perfect knowledge of all these, you'd still be in trouble. And why is that? And that's really a mathematical question. And why is that? Really goes back to 1963 with the notion of chaos. And here is a stamp from, I think it's Guinea. They seem to very much like physics and mathematics and things like that, that celebrated the death of Ed Lawrence in 2008. Ed Lawrence has very strong influence, and in 1963 he wrote a paper, very influential paper. He says, he started actually with a convection problem and simplified all the way down to 3 equations. And that became a problem that had no relevance for the problem he started with. But he noticed there was something very strange in the system when he studied in more detail, more mathematically. It transformed into a purely mathematical problem. The equations are very simple, 3 equations, dx dt, dy dt, dz dt. These are what we call ordinary differential equations, just about the simplest one, the simplest type. Except they have nonlinearity. Instead of x and y and z being by themselves, there are 2 places where they make a product, nonlinear. It's called what we call nonlinear. And nonlinearity have a very drastic effect on the solution. And when you run that on this old computer at the time, you can do it on a smart watch and things like that. It's a very simple system. He noticed something very remarkable that he fully understood at the time. That was also quite remarkable. So let me tell you what we're going to do. These are equations that if I give you the value at a time t equals 0, think of it temperature or something like that, you can run them and know the value at a time later. And there is no noise, there is no problem. It's something that we know for sure. There is one equation, that's what we call deterministic. It's fully known in the future. So if you know here at time t equals 0, I can go all the way to this position at time t, and since it's 3 equations, I can represent that in 3 dimensions, x, y, and z. So I can run the system, I can just let it go and see where it goes. And this is where it goes. When you let it run, the axes are turning for added visual appeal. And now, let it go, and the system, it doesn't go away. It doesn't go to 0 itself. It does something different, keeps turning around. What I haven't fully told you is that I actually started 2 solutions, 2 points, and they're slightly different initial data. So it's like if you want to run a weather projection, I would take the temperature today at 22 degrees, and I would run another scenario with 22.0001 and let them evolve. Right? So it started with 2. There are actually 2 points there, one green and 1 blue and 1 yellow. And this is what happens. If you let it run, very soon the points are going to separate. And they separate. I can start as close as I want. Eventually, they will end up at completely different position. And that was truly remarkable discovery for the weather system. Ed Lawrence was a meteorologist. He was interested in the weather, not so much in the climate, but in the weather for sure. So if I just look at one of the variable x as a function of time, for instance, and I start with the 2 points exactly at the same one, I wouldn't see any difference. But eventually, at time 20 or something in arbitrary units, you'll see the 2 diverging, and you'll see right here there'd be a different position. So if this was temperature or rain or anything like that, if I run the model, I don't know the difference between, is it really 24, 24.000001? Well, whatever I choose, even if I had perfect knowledge, a little bit of difference would tell me that, well, 2 weeks later it would either rain or it would be sunny. I have no knowledge. It's impossible to know. It's mathematically impossible. Okay. I would need perfect knowledge and perfect ability to do computation to do that. But every single measurement is initial data would come with a little bit of difference and error. There is nothing we can do about that. So this 2 weeks window is what stops us from doing any good weather prediction past 2 weeks. Maybe we'll be able to do a few, maybe another week. But we know for a fact mathematically we'll never be able to predict the weather for a year's time. We know that. The numbers are very clear. And in his paper, Lawrence says 2 states differing by imperceptible amounts may eventually evolve into two considerably different states. In view of the inevitable inaccuracy and incompleteness of weather observation, precise, very long-range forecasting would seem to be non-existent. It was very clear, completely understood the problem. A few years later, he wrote another famous paper saying that the flap of a butterfly could trigger a tornado many years later, the difference. And that was the amplification of this effect. And you know it's important when they start making bad Hollywood movies with that, with puppy-faced actor. So it really came into that knowledge, not only as a culture, but really completely changed the way of thinking of everybody doing climate and weather. Now that was in '63, and people understood at that time that it was important, but they still used the same model to try to see, okay, now we know we can know precisely, can we use that? Can we use that knowledge? So the idea is to do what's called ensemble averaging. I said, I don't know where I'm going to start, so I'm going to take a bunch of points close by together. Maybe it's 24 degrees today. I'm going to try all the temperature between 23 and 25 and run my model with that. And if I do that on the Lorentz attractor, it's called a chaotic attractor, if I do that, I can have different scenarios depending on where I am. I can start with a bunch of data here, and I look at the evolution, and 2 weeks later, I'm here. And basically, if I look at the center of here, it's still the center of that blob. So I know that I will have a good knowledge. It's very high predictability. I know that the trajectories have not gone too far away. I can have medium predictability if I start doing this. I could have very low predictability if I start here and all the solutions diverge. So this is a way to quantify our uncertainty. So you don't run a single model. You would run a model with very close but different initial data and look how far they diverge. And you say, well, since I don't know my initial one, my predictions stop at a certain time. So you can quantify how much you know about the model. It's this idea of ensemble average that's so important. And this actually is from a paper by Tim Palmer, also from Oxford, who's done a lot of work on this type of problem, trying to find ways to use this idea to a benefit rather than being an hindrance. Okay, so what's the final picture in terms of climate? This is the result of the Intergovernmental Panel on Climate Change. It was July 2014. It's the 5th assessment report of that panel, the IPCC. And they do exactly what I told you. They start here, 2010 or 2014, and they run the model with different scenarios. This is the model where people are responsible, and this is the model where people are, they are, I would say. So it's different scenario. And you see the scenario leads to very different. As you've heard in the news, whatever we do, even if we start behaving, there'll still be some increase. But otherwise, inevitably, we do that, with very likely. And these breadth and average are all coming from this idea of ensemble average all the way to 2100. So you can say, well, 4 degrees, that's okay. I mean, I'll water my lawn a few more times, right? But if since you've done all that computation on that fine grid, you have information about the climate change on average in all these different positions, these different places. So you can go back to your data and look at the evolution of the temperature under these two scenarios, and you see that this is where we behave. We still have increase everywhere. And that's what we are facing. And what we're facing are temperature increase up to 11 degrees close to the pole, So it's true it doesn't increase that much, but that's because the pole don't change that much. Or the oceans don't change that much. But the rest of the land has dramatic increase. And the theory has become quite reliable. I mean, there's been a lot of evolution, very quick evolution over the last 5, 10 years or so in terms of understanding what are we actually saying, are we sure about what we're saying, and so on, that community. That there is very little doubt now that that's what we are facing. Okay, so I want to stop about the climate here and move to other problems of application of modeling. I said, well, since we have all this sun, maybe we can try to find a way to be more responsible with it and try to do something about climate change. And I want to tell you a little bit about modeling that I've done over the last few years on photovoltaics. So whatever we do, we know that photovoltaics using the sun is going to be part of our energy portfolio. And today, the silicon technology, the silicon panels that we see everywhere, it's really the dominating technology. But it's very restricted in many ways, not as flexible as we'd like. And so people have been looking for a while to different type of photovoltaic. And that search has not been doing too well. I mean, a lot of people in a lot of different departments find alternative, but nothing really came to challenge the silicon technology. But that was until 2 years ago, when the group of Henry Snaith here in physics discovered that certain type of material they use in some of these photovoltaic cells, they use just by themselves has remarkable properties. And so we started actually 4 or 5 years ago with, thanks to the Oxford Martin School, which fund this type of collaboration within Oxford, to look at the mathematics, the modeling of this problem with Henry Snaith, trying to get some insight into this process. So let me give you the general picture. We measure a quality of a photovoltaic cell in terms of efficiency. It says how much energy can I get back from the sun. Okay? And so it's a percentage of energy I can extract out of light. And here we're just going to be interested in the silicon here. Gallium is arsenic is very good, but it's quite expensive. And here is the evolution of the silicon technology from the 70s, about 12, 15%, all the way to now 25%. And you can buy now the silicon, reliable silicon 20% from Chinese manufacturer. And they've done a great deal to actually reduce dramatically the price of silicon. So silicon will be with us and will be used. But as I'll show you, we want to have other technology for the purpose. Now, forget about all these. I just want to point out here, this is where we started in 2012. And we started around 15%, Henry Snaith's group. And now, actually last month, people have shown that they can have 20% in 2 years efficiency. It's very rapid growth. But it's not so much that it's, so now we know that these cells are potentially very efficient, but it's how they're made. The silicon is, so you have to grow crystal of that, it's very rigid. But the perovskite, you can actually just lay them down by different technique, vapor deposition, spin coating, which are very cheap way of doing it. Okay? So this is one of the modeling problems that we worked on with Henry. It says, okay, I know that I can lay down my perovskite, that miracle compound that works so well, but when I do it by vapor deposition, instead of being all flat, it has a lot of holes. And you can see, well, if it has a lot of holes, you're going to lose a lot of coverage and efficiency and things like that. So when you do that, you start making a lot of holes. So the problem is a problem of material. It's a problem of de-wetting. It's just like when you have a bunch of water on a table, the little bubbles start making bigger bubbles and things like that. So we look at that problem from that perspective. So it could be good, because if it doesn't fully cover, then you can say, well, I could use these and I could make windows, for instance, right? Because the light would still go through and I would still get some energy out of it. That's a good idea, but it looks like that, really. That's okay, but really, who wants to live in a brown building, right? So this is probably not going to be very popular on the market. So we went back and looked at the problem in more details. And we created a little model. I'll just give you the basic idea of the model. What we want is how much, when we lay down these, it's called annealing, but it's really called cooking. If you want to make brownies or things like that, you put it in the oven and you heat it up. You put a layer, and then you heat it up in an oven, 100 degrees, for 60 minutes, just like a cooking recipe. And what happens, the solvent evaporates and forms this structure that you want at the end. And the only thing that you can really control is the temperature and the thickness of the film that you start. And you know, if you make brownies or things like that, it might be very dry or very moist. Well, you have the same type of problem. You can do the same optimization for brownies. So what we did is say, okay, our layer is really a full layer. It has holes. And each of these holes, the total have a certain diameter and certain length. And we can write a full energy for this system depending on the different radius. And each radius, we know from fundamental physical principle, can change the size. The hole can change the size and interact with each other. And if you do that, I'll spare you the detail, but the problem is not too hard. I mean, it does require putting things together, but it's not too hard. And when you do that, sorry, let me go back here. When you do that, you get exactly what you want. You get the coverage as a function of the temperature and as a function of the film thickness. So you know how much thickness you need and what the temperature you should set your oven in order to get a certain level of coverage. And here the boxes are actually the experimental data, and the curves are what we predict. I said, oh, that's very interesting because you can really optimize your coverage. But then we talked with Henry and Henry's group, and he says, but look, we can do much better than that. Sure, we can optimize the coverage, but now we can go back to the problem and we can choose the right conditions so that the coverage is what we want. The holes distribution is exactly what we want, so that as the light goes through, it has a given color. Because the light is going to refract in different ways for different wavelengths and so on. And so this is what he actually made with his group. Okay, so now you have a technology that allows you to have a piece of photovoltaic cells a given color, and that you can put on windows and things like that and get maybe not 25% because there is still a lot of light, but you get 5%, maybe 10% soon. Okay, so you can have buildings like that where you have beautiful blue buildings, and you still collect the light as you go along. So it creates a new market, a new way of using solar energy. So we patented that. I don't know what's going to happen with that, but this is the kind of thing that you have to do. And we applied the same type of idea to different contexts. I think it's a good example because not only it has some predictive values, but really the mathematical models was part of the creative process in understanding the material and coming up with alternative of what we can do with it. Okay, so part 3b, the second example, the first one was aiming at saving the planet. Now we try to save mankind with mathematics. Let me tell you a little bit about the brain as it was advertised in the title. So there is a lot of wonderful mathematical problem with the brain. I'm going to concentrate on one that's not the kind that you hear with this huge big initiative, the Human Brain Project and things like that, which is try to understand the connection. I'm much more interested to see the brain as a real physical entity. And so my initial motivation was trying to understand trauma and brain injury, traumatic brain injury. It can result of unhealthy sports events, or car accidents, or stroke, or things like that. What happens in this case, invariably, what happens is that part of the brain becomes depleted of oxygen, and then you have an imbalance of ions, and the tissue starts swelling. Okay, this swelling can be very dangerous, as I'll show you in a second, and sometimes you do have to open the skull and do a craniotomy to relieve that part of the swelling. So we really wanted, I find that very interesting, but because once you know that, if you know the geometry and the change of geometry, then you can try to understand what happened all the way to at the axon, as the axon has stretched. Okay, what is the damage that's done at the axon and so on. All these are very important, not only for accident, but also in a lot of different disease, epilepsy and things like that. So when we've been thinking about this type of project for a couple of years, and together with Antoine Jerusalem in engineering, we decided to create an informal group we call the International Brain Mechanics and Trauma Lab. We started that in 2013. Try to pull back different specialty, different expertise from different fields to address this problem, because we quickly realized that you need to have the medical doctors, the biologists, the physiologists, the engineers, the mathematicians, and all that all together, because these are very, very complex problems. So I'll just tell you about one of the problems that we're working on. Now, this has grown to an international network of scientists in the world trying to answer some of these problems. I just want to look at the simple problem, or there's no simple problem when it comes to the brain, but the problem of swelling. And here is a swelling of a brain of a rat that was induced a stroke in the right-hand side. And we wanted to understand what actually happened. It's very well described in the physiology textbook and so on. But again, just like Kelvin says, there is no numbers attached to it. There may be measurement, but there was no way really to try to understand what happens, what is the sequence that happens. So what we did is we combined both fluid mechanics, solid mechanics, because you have a soft tissue, and the electrochemistry, which is the balance of ions and interaction of ions and electrolytes, to try to understand that. And we created a model with a quadriphasic theory, that means a 4 different phases interacting with each other, to try to understand that. And it's really the PhD thesis now of Georgina Lang that she finished yesterday. I think she sent the thesis. And that's also with Dominic Vella and Sarah Waters. So the first part was to understand the swelling. And so we built this model and fitted a number of parameters in independent experiment. And then we went back to some data that people do on very, very controlled system. And we saw that we could have a very good match of them. I'm not going to go into detail. But based on that, we really understood the different effect of different components of the swelling process. That was really the first step, was to create a model that would just explain the swelling. And when you do that, you can go to the next step. It says, okay, now I can induce a damage in my model. I wouldn't induce damage on poor little rat or anything, but at least on my model, and I can see if I can predict this type of event. Okay, that was the second step, trying to do the damage. And the third step was to say, okay, now how does the damage propagate? Because that's where we really started. And the damage propagates the following way. If we start with a brain and all these red dots are capillaries, if you have a lack of oxygen at some point, you restrict the capillaries, what you'll have is that the tissue is going to swell. And when it swells, it's going to compress its neighbor. And if you compress enough its neighbor, they don't give you oxygen anymore in the tissue. So they're going to die again, and they're going to start swelling again. Okay? So these swell again and compute, and so the damage propagates like that. This is how swelling propagates in the brain when it starts. It push each other, so it prevents the other guys next to you to have oxygen. They die or they're very unhappy, and so they start swelling again, and so on and so on. So we wanted to know how this damage propagates, and we build a model based on that, and we look at 2 scenarios where the skull is not open, and we look at, depending on parameter, the critical stress at which the capillaries will be squeezed, and as a function of the initial size of the damage, whether or not it will naturally propagate to the system. And we see that in this case, if the damage is large enough, it would always propagate if the critical stress is large enough. However, if you do open, it has a simpler geometry. I show you that for picture, but the geometry is much simpler. If you open this, you relieve part of the stress, and then the damage stops at a certain point. So this is a conceptual model. It has no direct predictive value, but it shows that we understood all the steps, all the critical elements that came in the problem. And in the process, we took away some that were not important, that were thought to be important. So now we can go back and implement that in the correct geometry, and that's the work that we're going to do in the coming years. We also look at problem of brain folding. That's another story. I want to go on to my last application, try to keep on time, which is seashells. So obviously, I'm not going to try to save mankind of planets working on seashells, but they're there, and they're quite nice. So the motivation was really for the beauty of it, as I said. I can't really justify on any other, well, I could if I have to write a proposal for an agency, because we become really good at that. But between you and I just do it because I think the problem is beautiful and interesting by itself. It's really curiosity-driven. And it's often in teas, as we can talk about that, but it's often by problems that are curiosity-driven that the biggest leap comes. So I have no problem doing that. And what is the problem? So this is work with Derek Moulton, who's in mathematics, and a biologist from in France, Régis Chirac. So what is the problem? Well, here is a seashell. I wanted to show you with the cam, but the cam is not working. Here is a seashell, and here is another one. And they're very beautiful shape and all that, but some of them have what's called morphology. You know, they have this spine and on top of them. And we wanted to know, can we explain these? People have been describing that for hundreds of years, spine teeth, rib that, and all that. There are plenty of paper. Very important for evolutionary process because it helps you to classify, see the trees and structure and all that. We wanted to see what are the minimal processes that can explain the creation of this shape, that can create these patterns. What is the morphogenesis process? So the first part was to really try to understand the main geometric shape, the overall shape of the seashell. And we built a model based on that that tells you if I know the growth process right at the edge of the seashell here, at the opening of the seashell, then naturally it would create one of these basic shape. Okay, so I'm not interested at the pattern there, I'm just interested in the global shape. That was the first step. Now, after that, we say, okay, now how is the shell created and how is the pattern created? And the basic idea is the following. You have an animal, most of the time before they die, inside, the mollusk, and it's a soft tissue, and the way it creates its shell is by coming out, going on the edge, depositing a new material, accreting new material that get calcified, and then retreating. So what you have is a soft tissue that goes on top of a hard tissue, and then it goes back, it changes boundary, and then the next day it comes out and does it again. Next day it comes out. So what you have is you have something like that. You have the mantle that comes out, goes on the aperture, and then lay new material. Now, the animal itself grows at a certain pace, and the accretion process is a different mass increase. There are two different processes. One is for the soft part, and one is for how much material I'm going to put down at each level. Now, if you do that, you start with one, and then you go out and put a little one. Now, if the soft mantle grows faster than the aperture, it doesn't fit nicely on top of it. So it can make a nice shape. And just like you have an elastica or something like that, or a rubber band, and you push it, it cannot really put itself at the right place. So what's going to happen is the following. If you look at the edge, the mantle comes and going to try to adhere, glue on itself, and put a new layer. But it's too long for the shell edge. So it's going to do this little hoop here. It's going to buckle. And that's how it's going to present. It's going to put the new layers. And comes out, it comes back in, and then goes back out again. So if you have a little problem here, it's going to get amplified this time. So the equations are quite simple again for this type of process. It's an evolutionary process where the boundary evolves with the system as time goes on. So it's a non-standard problem when it comes to mathematical modeling, but it's very easy to go on and simulate. And this is what you get when you vary the parameters, the two important parameters. Depending on the parameter that you have, you either get this very sharp spine or you get very wide one. And so depending on these two parameters, the growth rate and the stiffness, or stiff is your mantle, then you can easily map all the shapes that are around, that are found. You know, either you have like a beachcomb, beautiful, very, very, very thin spines, or very wide spines like this one. So this is one way to reduce a lot of knowledge. And we say, okay, now we have a model, but if we want to push it, can we apply the same idea to other patterns that are found without fiddling anything with the basic idea? So we went back and say, well, there is another pattern that's found in seashell, in ammonites, Now, ammonites have been extant for about 100 million years, so obviously we don't have that much data on the living animal, but we have a lot of data on fossil records. And people for hundreds of years have been looking at these ribs on ammonites, classify them, look at evolutionary trend and all that. A lot of very nice work on that. He says, if the only thing I know is how fast these aperture opens, can I actually predict the form and the shape of the pattern? And so this is the result in blue line of the simulation by the same type of equation, based on just the knowledge of the expansion rate of the inside. If I know the red one, I can compute because again, the mantle part, the soft tissue, is going to grow faster, and then it's going to be pulled back and so on. Essentially, really with the basic simple principle. And this was just accepted last week, actually, this week. So what you can do is you can go back to all the biology textbook, and you can map, based on the parameter that they have, you can predict all the shape and all the feature that they observe based on that. And now you really have a tool based on mathematics that tells you, contains a very simple model, what you should expect from the patterns. So I want to conclude with a few thoughts about what are the new challenges of a mathematical modeling. I'll show you a little bit what they are. Turns out for a lot of complex biological systems, what we have nowadays is the system we look at, climate, brain, or anything, are all multi-scale. The smaller scale has an influence on the larger scale. They're all multi-physics. We have to have chemistry with physics, with ice modeling and all that. They involve many different processes. There is always a component that's stochastic, and stochastic systems have become more important. We should really look at deterministic problem, but things have natural noise, and we should compute directly with that. Things evolve from dynamic network, for instance, the connection in the brain and things like that. So there is a lot of work now in the modeling for networks that's very important. And all these problems, these complex problems, always need the integration of many disciplines, which makes also Oxford particularly good for that because there is a natural connection, a natural way to interact between different disciplines. One last slide. I try to show you that mathematical modeling is a discipline, it's part of a craft, but it's also a tool for invention and creativity. It's needed in facing all the new challenge, climate and all that. There is an aspect that I didn't talk to you about, is that all these modeling aspects also naturally create interesting mathematical problems on their own. It's a natural source of interesting creative problems, even for pure mathematics, and I can show you examples of that. And if you don't believe me that mathematics is everywhere, as you go out of this building, you'll see that on the glass panel over there, there is a very strange form. It's a gumbox. I'm not going to tell you too much about it, except that we'll have a lecture later this year of the inventor of the gumbox and all its beautiful mathematical property and how it's related to turtles. Then if you go out, you'll see the Penrose stylings, of course, that I'm sure you've seen. And I encourage you, if you have a chance, to go to the lecture tomorrow of Roger Penrose on architecture and mathematics, with this style as an important piece. And if you like stamps, there'll be a Christmas lecture by Robin Wilson on which is going to show his collection of mathematical stamps. And based on that, I thank you very much for your attention.